Limits of exponential and logarithmic functions. Our objective is to examine limits and continuity of exponential and logarithmic functions. Exponential functions. In general, that is, with an x as the exponent and a number in the base, such as y equals a to the x. Now, most of the time, we are going to be dealing with the natural exponential function, y equals the number e raised to the x. It is extremely important that we know how the graph of y equals e to the x looks. Now, this is y equals e to the positive x, exponential growth. We must remember that because e is a positive number, remember that e is approximately 2.7, but it is irrational, so it's a decimal that keeps going and going and going, very much like pi. Anyway, it's always positive. So while it looks like it's getting to 0 here, it's actually just getting closer and closer and closer to 0. There is a horizontal asymptote that is not sketched in that we want to remember, and that is y equals 0. So as the graph moves to the left, the function's getting closer and closer to 0. We can remember that as x approaches negative infinity, e to the x approaches 0. It gets closer and closer to 0. That is an extremely important thing to remember about that exponential growth function. We also want to remember that e to the 0 equals 1, just like all numbers but 0 to the 0 equal 1. So when x is 0, the point 0, 1 is on the graph. Also, e to the 1 is itself, so the point 1, comma e is on the graph. Those are two must-know points that are on the graph. Now, if we have exponential decay, so this one right here, the way that it's drawn, is exponential growth. But if it's y equals e to the negative x, that's going to be exponential decay. Still, if we plug in 0, we get 0, but that's going to be coming down the other way. That's going to be the exponential decay function. Either way, we must be aware of what these graphs look like and that there is this horizontal asymptote at y equals 0 unless there is a shift in the graph. Noticing how this function looks, remembering how this function looks, we can tell that this function is continuous on its entire domain, which is all real numbers. And as for limits, this is a well-behaved function, so substitution works quite nicely. The limit as x approaches c of a to the x equals a to the c. We're just substituting the value of c in for x. Now, noticing that the graph is continuous on real numbers, but where it goes, we can take a look at the other limits, such as we already examined what happens to the left. As x approaches negative infinity, the function gets closer to 0. As the graph moves to the right, so as x approaches positive infinity, this function goes up. The function goes to positive infinity. And of course, because of the point 0, 1, the limit as x approaches 0 of e to the x is 1. That's merely just substitution of e to the 0 equals 1. Now, these properties right here are important properties that we remember about how to work with exponents. Let's take a look at logarithmic functions. Logarithmic functions, basically y equals log base a of x, where a can be any real number that's positive, or what we're going to use mostly, the natural log function, y equals natural log of x. This one is the log with base natural number e of x, just written in the shortcut way. Notice what this graph looks like. Kind of like the exponential function, how it looks like this branch is disappearing and goes away. It really doesn't. There is a vertical asymptote on the log function. The vertical asymptote, x equals 0. So as we notice, we can't say x approaches negative infinity. The closest it gets to the left is towards 0. So to the left, this is to the left as x approaches 0 from the right of natural log of x, because the function goes down, we're saying that limit is negative infinity. That's going down. Now to the right, x approaching infinity, the function is always going up, so that limit is positive infinity. Notice the 2 points that are on the graph, very important to remember. 1, 0, because the natural log of 1 is 0, and e1, because the natural log of e is 1. You must know how this graph looks and behaves, and what these points are on the graph, these 2 points. Notice this graph is continuous on its domain, which is all positive real numbers, and that the limit behaves quite nicely. It's a well-behaved function that we can simply substitute into into x, that variable where x is approaching c, and get log base a of c. Now, take a look how these 2 points, 0, 1, and then 1, 0, they are switched. And 1e and e1, they are switched. It's because exponential and logarithmic functions are inverses of each other. Now, before I go away from this page, notice that these properties are also important to know for the log properties. The inverse properties. If f of x is e to the x, its inverse, f to the negative 1 of x, is natural log of x. And because these are inverse functions, when we do the composition of them, because remember, inverse functions, when we do f of g of x, we get x, or g of f of x, we get x. That's if f and g are inverses. And that's what we're doing here. The composition of the 2 functions. Natural log of its inverse function leaves us with just x. And e to its inverse function leaves us with just x. I like to think about it as when I see the natural log with e, I'm left with just the x, and when I see the e next to the natural log, I'm left with just the x. Now that's a very simplified way to think about it, but it's helpful. Notice these 2 graphs. Our graph A is when A is between 0 and 1, so we've got our exponential decay going on right here. This is our decay graph, and our exponential growth graph. Of course, the blue is the exponential, and then we have our mirror line for inverse functions, y equals x. So when the blue is flipped over that line, it makes the log graph. And here's the other log graph, the inverse of that exponential growth function. Let's take a look at some examples. Find the limits. The limit as x approaches 1 of natural log of x over e to the x. So remember, if we can, we always want to just try substitution. Let's give it a shot. Natural log of 1, let me write that properly, 1 over e to the 1. So that makes natural log of 1 over e. An easier way to write that is natural log of e to the negative 1. And then using our inverse property, we're left with just negative 1. And substitution worked just fine, as long as we remember the inverse properties and laws of exponents. How about this example? Can we plug in 0? Let's see what happens. 1 minus e to the 2 times 0 will make 0, and that makes 1 minus 1, and that makes 0. So that's not going to work quite well. So we think about some strategies that we've used to manipulate the way the function looks, so that we can work with it better. Now, it's not completely obvious at first glance, but this is a perfect square, e to the 2x. Knowing our inverse properties, we know that, or our exponential properties, excuse me, e to the 2x is equivalent to e to the x times e to the x, because when we multiply exponential functions with the same base, we add the exponents. So this makes e to the x plus x, which of course is e to the 2x. All that to say, this is a difference of squares down here. So I can rewrite this limit to look like this. Limit as x approaches 0 of 1 minus e to the x over 1 minus e to the x times 1 plus e to the x. And now we have a common factor that we can divide out and probably won't get 0 in the denominator now. Let's try it. 1 is of course left when we factor out from the numerator, so 1 over 1 plus e to the 0, and of course we remember e to the 0 is 1, so 1 over 1 plus 1, or 1/2. And we've done it. Thanks for watching.